Oh, come on. There we go. Everything's awoken now. Not me. It is a very, rainy day, and this is one of those days that, like, just like a cup of cocoa and binging some cartoons. This would be a good day for that, All right, but we're gonna do something even more exciting. We're gonna talk about tension members. Okay, this is gonna be our second tension member example, and I'll give you a little bit of background. I've taught this class every year since I've been here, and usually what I do is I tension members, there's a lot of different things that we put together, and then like the last lecture, which is sort of the culmination of everything we have been talking about so far. Because there's so much stuff, I've always thought, let's go ahead and do another one to make sure that we're comfortable with this. But this year I decided to do something a little bit different, because our second example, I'm going to add some things, and you'll see what I mean when we get into that. I think all the outstanding homeworks are graded other than the one that you submitted today. You got one today due Monday. Okay. Sorry. This sinus infection. Woo. Did everybody get the code? Okay. Okay, so I'm not going to spend a lot of time on the slides because a lot of this is recap. However, there is one thing I do want to talk about a little bit, and that's braced frames, and you'll see what I'm getting at here in a bit. Okay, I think I accidentally skipped one slide more than I wanted to. Yep. Okay. So keep in mind we're still investigating LRFD limit states. We're still going to be using our LRFD load combinations, although today we're not going to use them because the loads that we're going to use are already factored. Not really a big deal, just trying to save a step here in the in-class example. Man, why am I skipping two slides? Okay. Our tension member limit states, we have two right now for strength, gross section yielding, that section fracture. We're going to add one next week on block shear rupture after we discuss design, which that's going to be our our main topic of discussion next week is design. FY and FU, we can look that up in table 2-4 for shapes, 2-5 for plates and bars. We have our complete expression for net area, the gross area minus the area lost due to the presence of bolts plus any necessary stagger factors. That's for bolted connections. For most welded connections, gross area equals the net area. And then shear lag factors. Okay. So I want to explain the example I'm going to show you all today, and I want to do that by talking about lateral bracing. If you remember, during the very first lecture in the class, I showed you all some images of this building being constructed. And if you remember, there were these diagonal elements that were in the building at certain key locations. And their job is to withstand lateral effects. Now, the two most common lateral effects that we need to deal with are wind and earthquakes. I'll say that in this area of the country, we don't have too much of a high seismic demand. But everybody's got to deal with wind. Without some means of resisting lateral loads, the building's going to be subject to collapse. Now, there are a number of different ways to withstand lateral effects. The two most common in structural steel design is to use either a moment frame or a braced frame. Now, a moment frame, what it does is you rigidly connect the beams and the columns such that you can transfer moments and shears across them. So it's like the difference between a truss and a frame last semester. Moment frames would be treated like frames. Brace frames are kind of like trusses, okay? So the idea is that we place diagonal braces somewhere in the building in order to withstand those lateral effects. We don't place them everywhere, we just place them where we need them. These are some, more dedicated images to kind of show you what diagonal bracing looks like. These are a couple of different bracing schemes that you could use. So these inverted V's This is an option, sometimes called chevron bracing. You can have X-style bracing. This is what I would call two-story X bracing or super X bracing, because the X shape actually crosses multiple stories, which is possible. I have here a couple of, I guess, more comprehensive bracing schemes. They're like what pattern that we choose and which one we're going to use for a given building largely depends on the load demands on the structure. In other words, like more braces for more load. Also, the architectural needs, the client needs, and the client preferences and whatnot. So, the reason I mention that is because this is going to be our problem for today. We're going to go back to last semester. We're going to do a truss. Everybody, that should be exciting. So what we're going to do is we're going to analyze this truss, and we're basically going to look at this member right here, and we're going to see whether or not this member is adequate to withstand the applied loads. Now, I'm being somewhat choosy here in my notation, okay? and I want to explain that. So last time, if you recall, this is what we're trying to guarantee, right? In other words, we're trying to guarantee that the factored resistance is greater than or equal to the factored load, okay? Now, let's talk about this term right here, that PU. PU is the factored load that the member in question has to withstand. Does that make sense? Like, if I'm looking at this member and I'm yanking on this member, that's how much load that member is seeing. Does that make sense? The point I'm making is that is not the same as this or this, okay? These are the applied loads on the structure. The structure will respond by developing internal forces inside all these members. We got to determine what that is through structural analysis. Okay, does that make sense? So, okay. Excuse me. So this QU, I'm using that to sort of represent the external loads applied, and PU is going to be the internal force inside the brace. Okay. Now, the member itself, I'm going to say it's an 8 by 6 by 7/16 bolted through the long leg, and here's the connection scenario. So with that, I think we got enough info that we can go ahead and jump right in. Okay. So this is our member, okay? Or this is our member, and this is our structure. I did tell you that 836 steel is used and 3/4 inch diameter bolts. So, so that should be pretty straightforward. I think that the evaluation of the tension member itself will be very doable for everybody here. But I think it's probably been a while since we've looked at the structural analysis, right? So let's do that, okay? Some of you had that last semester. Some of you, maybe it's been a little longer. Okay, so let's look at this part. Okay. Okay. So, we need this member, okay? And I argue that probably the simplest way of doing this would be to compute the reactions, then maybe do a method of joints analysis right here. If we do a method of joints analysis right here, that'll give us the force inside this member. Does that make sense? Okay? So, let's see. This roller, how many reactions do we have?
One.
Is that horizontal or vertical? Vertical. This one has 2. So there's a vertical reaction, and a horizontal reaction. Anybody know which one's easiest to solve for right now? Horizontal. right? Because if I have 100 going to the left, 50 going to the left, what's this reaction? There we go. Is that fair? Okay. Now, would everybody agree that a method of joints analysis of this joint right here will give us the force inside this member? Does everybody agree with that? So in order to do a method of joints analysis, I need this reaction, right? What's a simple way of getting this reaction? Take sum the moments about this point right here, right? So we will sum moments about the left support. Okay? What do I have? 50 times 15, 100 times 30, right? And then there has to be resisted. So this needs to go, which direction does this go, up or down? Down, right? Because this is rotating this way. This has got to rotate the other direction. This has got to go down. So RY times 20 is going to be, okay, 50 times 15 is 750, 100 times 30 is 3,000, so 3,750. Did I get that right? And by the way, what's this reaction going to be? Up, yeah. So we don't have to worry about that, but, you know, there we go. All right. So let me do me a favor. Let me drag this down a little bit. Okay. So now what I'm going to do is a method of joints analysis. Before I do that, though, is everybody comfortable with this? Okay. And again, I want to make sure that this is clear that this load and this load are already factored. So we don't need to do a 1.2 dead or a 1.6 live because these have already been factored. We are treating these as factored loads. So whatever the response is inside this member, it's already factored as well. Okay? Everybody okay with that? Okay. So let's see. Right, and then we have a member and a member like that, right? This member, what's the slope ratio for this, by the way? 345. Right, so this is going to have, let's see, a horizontal and a vertical. This one's going to have a vertical, right? So, which one do I solve for first? Horizontal. So if this is 150 to the right, this is 150 to the left. And by the way, what is this going to be? Everybody do that one?
140.625.
Wait, what? Well, no, hold on. Wait. So let's see. So we'll call this FX, Fy. Fx is to 4 as Fy is to 3. So Fy is 3/4 of Fx. So it's just 3/4 of this. What's 3/4 of that? 112.5. So therefore, what's the internal force inside this member? How do I do that? Break out that old Pythagorean theorem, right? So, and that, by the way, that is our load inside the member, right? That's the force that the member is seeing. And so what is that, by the way? 187.5. Do I have a second? Okay. Okay. So, break out a marker here. No worries. So right here, this 187.5, that is the load that this member needs to withstand, okay? So now what we need to do is figure out, can this member withstand it, okay? But I don't want to skip ahead. I want to make sure that everybody understands what I'm talking about, that this is the load that the member is being subjected to. Not 100, not 150, but this, okay? And by the way, is it tension or compression? We're looking at tension members, right? So it better be tension, right? Sound good? Okay. Okay. Let's make this a little bigger. Okay, so this is our tension member, and I'll put here bolts are through the long leg on this one, which, unless otherwise stated, that's the most common. Like if you have an angle that looks like this, chances are you're going to bolt through this side and not that side. Okay, so unless otherwise stated, you can just assume the bolts are through the long leg, I think, in most instances. Okay. So the last part was review of CE 312. Now I need your help. So tell me what to do. We first need some properties for the angle, okay? We're going to get that in table 1-7. So somebody start telling me what properties you think we're going to need.
Gross area.
Okay, the gross area. All right, gross area. We are going to need the thickness, but that's just 7/16 of an inch, so we don't really need to look anything up. What else do you think we're going to need? Rmin. For an angle, which is that? Rx, Ry, or Rz? It's always going to be Rz for an angle. What is R? Well, okay, we'll get the values here in a second. What else am I going to need? I'm missing one. Okay, but, okay, think that through.
X bar.
X bar. I'm going to need X bar. And if the bolts are through the long leg, you're going to use X bar. If the bolts are through the short leg, you're going to use Y bar. So help me out. What is the gross area for an 8 by 6 by 7/16?
5.99 square inches.
Okay, what about RZ and X bar?
RZ is 1.31. X bar is 1.44.
Okay. So there's that. Okay. How about the steel? I think we said that this was A36. What does that tell us? Okay, FY. And FU. What are FY and FU? Yep. And FU is 58. Okay. Let's look at the connection. Let's look at the connection properties. First off, I know this, and so what does that tell me? Right, so if I know the bolt diameter, I know the effective hole diameter by just adding an 8. Okay. What about S and G? For our stagger factor. Exactly right. G is perpendicular to the load. That's this distance. The load's going this way, so G is this distance. That's 3 inches. This is 2 inches. Okay. I got 2 other values that I kind of want to figure out for this member before we start doing some math. The first is the length of the connection. What is the length of the connection? 14 inches, right? 1, 2, 3, 4, 5, 6, 7, out to out. So we'll call it 14 inches. Okay. All right. I have one other value that I need to make sure that I have for this member. How many checks are we going to make? We're going to make 3, right? We're going to look at gross section yielding, net section fracture, and what's the third one? So what do I need to do slenderness? I need the member length. So what is the length of the member? Let's go back to the truss. How do I figure out the length of the member? Pythagorean theorem. So And so that's going to be, what, 25 feet? Is that a useful value for our slenderness calculation?
No, 40 inches.
25 feet is 300 inches. Okay. All right. Now I think we can start doing some calcs. Okay, but before I move down, any questions on this? Okay, now we can start doing stuff. So, we can start doing some calculations if we want to look at what property do we need to compute first. We want to start looking at our strength limit stakes. And we can do gross section yielding now, but we can't do net section fracture. What we got to do? Find the net area. We have a staggered connection. So how many viable failure paths are there? 2. I'm counting 1, 2. Right? So, let's go through that. Okay, so net area. So, what I'm going to do, hold on. Let's just do a net area 1 and a net area 2. My net area 1 is going to be the one without stagger. In other words, let's just subtract 1 bolt hole. So that's going to be that. We'll say 3 decimal places just to make sure we're all on the same page. So what do we get for this value? 5.607. Okay. Now, what's my formula for the second net area going to be? But how many holes? 2. Right? So, right? So we have the gross area minus 2 bolt holes plus 1 stagger factor for 1 diagonal path. Okay. So how about this one? 5.37. Oh, I have a typo. Squared. S squared T over 4G. You squared yours? Okay. Do I have a second?
Yeah.
Okay. So which one is our net area? What's that? The smaller one. Okay. What's next? shear lag factors. Okay, so are we in a case 1 or a case 2 situation? 2. Okay. Now, because of all the work we've already done, we know that X bar for the connection is just X bar for the angle, which was that. So what is U2? 897. Are there any other cases that apply for shear lag? 8. How many fasteners per line in this connection? 4. So what's U sub 8 going to be then? 0.8. From these, which one's going to be my U value? The bigger one, right? Okay. So now what do I do? I've got my net area. I've got my shear lag factor. I can start doing my factored strengths. Ah, you go away. So I have my gross section yielding, my net section fracture. Gross section yielding was, remind me, what was that again? How do I compute that? There we go. And how about net section fracture? There we go. So this was 36 KSI. What was AG? And then I've got net area right here. And my U. Okay. Let's just do like 2 decimal places for these. So anybody got a gross section yielding value?
194.08.
Kips, right? And what about net section fracture? Say it again. 245.66. I got a little bit of a different value. 58. 209.53. That's more along what I got. Everybody got good? So, okay, I don't think I've actually used this term yet. Which one governs? Like, which one do I use to say that's the capacity? The smaller one. So, if you ever in structural engineering calculations see the term governs, that means that's the one that controls the design, okay? So that's the one that we're going to use. So in this case, VPN is that. Does anybody have any observations about this value? What does this value tell you in your gut, in your bones? Do you feel good about this member?
Yeah.
Why?
Because it's greater than PU.
And what was PU again?
187.5 kilos.
Yeah, see, this is how much the member had to withstand, and this is how much it can withstand. Pretty good, right? Okay. I feel like we're forgetting something, though. Slenderness.
Performance pressure.
I'm going to get, we're going to do that. I'm glad you said that. I'm glad you said that, because I want to do a summary statement at the end. What was it, 1.31? So because our R value is bigger than 1 inch, we know it's going to be good. What is our slenderness? So is that good? Okay. All right. So going to your point, I want to do what's called an analysis summary. So we do all this work and we get that VPN and is that, and PU is that. And that means the member is okay. What is the efficiency or the performance ratio for this member, by the way? 96.6%. That's pretty good. And L over R is 229.0. So I really do like having this at the end of your calculations because, let's take a look at this. Let's just zoom out. Look at all this stuff we did together. Look at all this. We did all this, but really, this little green box, that's the money. That's what matters, right? That's the money. That's the money, right there. The fact that our factored resistance is greater than or equal to our factored loads, and the fact that the slenderness is less than 300. That is really all we need to say about this member. So, what's our answer to this question? The question said, determine if the member below is adequate. Is this member adequate? Yes. That's our answer. Okay? Also, well, go ahead.
Well, I have a question for the whole thing.
Yes.
But if you had to do this again without the factored loads at the start, would you have to do an analysis for each type of it?
No, and I'm gonna. That's your homework. But it's a lot easier than that. It's a lot easier than that. I do want to say one thing though about that question. For your homework, really easy. For trusses in general, pretty straightforward. Where your question can get a little tricky is with beams, particularly with shear and moment diagrams. Because you can have a dead load and a lot like dead loads, live loads, and with each one you get a separate moment diagram, and the maximums on those moment diagrams are not at the same spot. Then how do you deal with the load factoring? We'll talk about that later. But, yeah. I'll also say though that in most practical scenarios you don't have to worry about that because we structural engineers love symmetry. We try and exploit it whenever we can. Whenever you have symmetry, it ends up not being an issue. Did anybody notice how I was kind of mean with this problem? That we did all this work for the net section fracture to get the net area and the shear lag factor and it ended up not mattering? I'm sorry. That happens though. That genuinely happens in the real world. Okay. Sound good? All right. I want to show you your homework and give you a taste of design for next week. So this is your homework. Okay? So a couple things. First off, so to sort of directly answer your question, when it comes to the truss, right, these are the same, right? And so what I'm suggesting is just factor this, then analyze the truss. Now, if we want to get philosophical, let's get philosophical, okay? If you wanted, you could do this one of two ways. Factor this, analyze. That's method one. Method number two, analyze for the dead loads, get a value. Analyze for the live loads, get a value. Analyze for the snow loads, get a value. Take those values, factor. You get the same answer. That's sort of my point. You could do it either way, and it wouldn't matter. You can do it either way because this structural analysis is linear. It's linearly proportional. Okay, does that make sense? Okay. Now, the other thing I was going to say is when it comes to the member, so this member is a plate, okay? So instead of it being an angle, it being a channel, a W section, it's just a plate, okay? It's just a plate that has a width of 8 inches and a thickness of 1/2, okay? I'll go ahead and tell you, you do not need to check slenderness limits for this problem. It actually fails slenderness limits. I'll go ahead and tell you. It's way slender. I think its L over R is like 600 or something. It's bad. And some of you are going, well, why did you pick a member that you knew failed slenderness limits? Let's just say when you get to the analysis and you get to certain parts of the problem, you'll see why. I'm just going to leave it at that. I'll give you one further hint. I'm talking about the shear lag factors. That's all I'm saying. Okay. Pay attention when you calculate your shear lag factors. Okay. I want to give you a taste of design. We're going to talk about this in much more detail Monday and Wednesday, but let's talk a little bit about design. Tension member analysis is given a member, assess the member's performance, right? Tension member design is pick the member to withstand the loads, right? We need to open up this manual with thousands of data points and sections and find the shape that is most optimal, okay? So before we begin, I have some ground rules. In this course, we will always strive to select the lightest member possible, okay? So how do we determine between two members which is the lightest? Well, which is lighter, a W10 by 49 or a W10 by 39? Why? The second number is lighter, right? Another way is whichever members have the smaller gross area, right? Smaller area means smaller weight, either way. The other thing is, I will constrain these problems a little bit in such a way that we'll all get the same answer. Like if I just give you a problem and I just say, give me a tension member that works, there's probably 50 different answers that are all right, okay? So there will be some constraints to make sure that everybody arrives at the same answer. Our second design homework is actually intended to open up those constraints a little bit, and you'll see what I mean when we get to that. But how do we design? Well, design means picking members, and picking members means we need some way of doing it. Well, how about this? If the resistance has to be greater than or equal to the loads, and I know what the loads are, let's take gross section yielding, 0.9 FYAG. If I know what the yield stress is, if I assume a grade of steel, I can divide and say that my gross area has to be bigger than that. That's a way of picking a member, right? Another way of picking a member is saying that the radius of gyration must be bigger than L over 300. That'll work, right? Anybody see a problem with net area? How do I deal with net section fracture? I mean, here's the thing. Like, the manual does not list net areas for members. We have to compute the net area. The problem is, with gross section yielding, we can solve for the gross area. With slenderness, we can solve for the radius of gyration. We can't really do that for net section fracture. Like, in other words, the net area is a function of the hole thickness, and if you're in design mode, you don't know what the thickness of the plate is. If you don't know what the thickness of the plate is, how do you compute the net area? You can't do it, right? The other thing is, what about shear lag? Like, if you're designing, how do you know what the shear lag factor is? So the answer is you can't really figure that out analytically, so what you have to do is just make a guess, okay? A very common guess is to say that the effective net area, in other words, take the net area times U, take that whole quantity, and say it's about 75% of the gross area, right? So remember what we do. We take the gross area, it drops a little bit to get to the net area, and then we multiply that times U so it drops a little further. I'm saying that a good estimate from there to there is about 75%. It's a guess. It's an assumption. It's an estimate. It's not accurate, okay? What we're going to do is use that as a means of picking a member, and then we go and analyze it, okay? So the idea is in design, we're going to use some guesses to pick a member, then we're going to evaluate that member to see whether or not it works, okay? The only other thing I wanted to say is on our efficiency. Whenever you're in design mode, if your efficiency is 90% or better, we're going to call it as you're good, okay? In other words, that's an effective enough design. It's sort of like spinning the wheel, right? Price is Right. Spin the wheel. If you spun the wheel and you have 95 cents, would you spin the wheel again? No, right? Because how does it work? You got to get as close to $1 without going over. What would happen if your efficiency was 105%? What would that mean? Bad thing. It would mean the load is greater than the resistance and the member is unsafe. So we want our efficiency to be as close to 100% as possible, but not larger than 100%. So if your efficiency is 90% or greater, that's good enough for design. And I'm going to leave it at that. We'll get this. We'll talk about this in more detail on Monday. That's all I got, everybody. Have a wonderful weekend. Try and stay dry.